Many curriculum designs start with a well-intentioned error. We look at a list of content to teach and immediately start planning engaging activities to cover it. We provide disconnected fragments of information to our students, hoping that if the activities are fun enough, deep understanding will naturally assemble itself. On the left is the result of that forward planning, a sequence of disconnected quizzes and events. On the right is an alternative, a single, rigorous performance of understanding. That cluster of disconnected activities defines the activity trap. It occurs when high student engagement masks low content mastery. Students remain busy, yet fail to demonstrate understanding of the underlying concepts. Grant Wiggins and J. McT identified a structural solution to this problem, known as understanding by design. They realized that effective learning architecture cannot be built chronologically from day one. It must be engineered in reverse. This diagram outlines their solution. We are going to deconstruct the anatomy of rigorous performance tasks and map the 3 stages of understanding by design, desired results, assessment evidence, and the learning plan, directly to the planning demands of the International Baccalaureate Framework. True learning requires intent. To guarantee that students arrive at a specific cognitive destination, we reverse engineer the entire curriculum, starting from the final performance and working backward to the very first instructional activity. We begin with Stage 1, desired results. Rather than compiling a list of facts to memorize, this step requires educators to define transferable understandings. We take a massive list of raw content standards and filter them to distill the core purpose of the instruction. In the IB framework, the input source varies. For the middle years and diploma programs, these outcomes are dictated by strict subject guides and objective strands. In the primary years program, they are derived from scope and sequence documents. Regardless of the source, these standards must be condensed into an essential question. This is a provocative, open-ended inquiry that provides the cognitive destination for the entire unit. A strong Stage 1 essential question looks like this. How well can pure mathematics model messy, real-world situations? Presenting this question on day 1 forces students to evaluate every mathematical formula they learn over the next month through a critical lens. Students evaluate the utility of mathematics itself while applying the specific geometric formulas. Without a targeted essential question, the instructional content lacks a destination. Students default to rote memorization because they have no conceptual framework to attach the facts to. Once the destination is set, we move to the central pillar, Stage 2. Here, we determine exactly what constitutes acceptable evidence that a student has achieved the desired understanding. That evidence is collected through an authentic performance task. This requires students to prove cognitive transfer by taking the knowledge they learned and applying it to a novel, realistic context. To build these tasks, educators use the acronym GRASPS. They define a real-world goal, assign the student a role, specify an audience, create a situation, define the product to be made, and establish the standards for success. Structuring an assignment with these 6 elements pushes the cognitive demand to depth of knowledge level 3 or 4. It forces learners past basic recall and into strategic thinking and extended reasoning. In a primary, grade 3 classroom, this looks like assigning students the role of ancient engineers, tasked with determining the best path to build a Roman road through a specific geography. For middle year students, it involves taking on the role of a community advocate who must evaluate and present the local economic and environmental impact of fracking to a simulated town council. By high school, a student might act as a materials engineer, running mathematical models to optimize fuel efficiency and terrain traversal for vehicles exploring Mars. Evaluating products of this complexity requires strict criteria. Educators use rigorous, criterion-based evaluation tools, like analytic rubrics, to measure the distinct strands of a student's logic. Under backward design, the summative assessment is not a post-mortem test given at the end of a unit. It is the structural anchor that justifies every piece of curriculum that comes before it. That brings us to Stage 3, the learning plan. This is the engineered pathway of specific instruction, practice, and scaffolding required to prepare the student for that final Stage 2 performance. The absolute first step of Stage 3 happens before any new instruction begins, the assessment of prior knowledge. Constructivist learning theory dictates that humans build new knowledge strictly on top of existing knowledge. We must first make the student's existing cognitive schema visible. This diagnostic data can be gathered through structured methodologies, such as having students draw concept maps or completing targeted self-assessment probes about their current skill levels. This chart illustrates the result. Incoming diagnostic data dynamically recalibrates the teacher's starting point for the unit, adjusting the instructional baseline to match the reality of the room. Practically, this prevents educators from wasting valuable class time reviewing skills the students have already mastered, or conversely, talking over the heads of students who lack the foundational prerequisites. A written learning plan is merely a hypothesis. It must be calibrated by the reality of the student's actual cognitive starting line. Once instruction begins, we rely on formative assessment. This is the minute-by-minute mechanism used to keep the learning plan on track toward the summative goal. Educational researcher Dylan William notes that ongoing formative checks act as constant navigational readings. If the learning is drifting off course, the teacher uses these readings to make immediate instructional adjustments. To design these daily interactions systematically, educators use the acronym WHERE-TO. The opening phases dictate the inputs, ensure students know where the unit is going, hook their interest, and equip them with the necessary content to succeed. The critical feedback phases require us to provide opportunities for students to rethink or revise their understandings and to evaluate their own progress. Finally, the adaptive phases tailor the instruction to individual needs and organize the sequence to maximize sustained engagement. Effective daily instruction engineers a tight, continuous feedback loop that drives the learner directly toward the authentic performance task. All of this architecture is bound together by a strict IB mandate, the transparent communication of assessment expectations. In the primary years program, transparency is achieved through co-construction. The teacher builds the success criteria directly with the students on the whiteboard. The teacher facilitates this by showing students strong and weak exemplars of previous work, asking them to analyze the differences, and having the class synthesize the critical features that make a performance successful. In the middle years and diploma programs, the strategy shifts toward decoding complex, program-mandated objective strands for older students. This is accomplished using formalized task sheets, augmented with task-specific clarifications. These clarifications translate the abstract language of an IB achievement band into highly actionable instructions tailored specifically to the scenario the student is working on. The timing of this communication is non-negotiable. Whether co-constructed or task-specific, the exact criteria for success must be visible to the student before the task begins. Supplying the rubric upfront eliminates the game of guessing what the teacher wants. It transforms the student from a passive rule follower into an independent expert learner who can self-assess their own progress. Viewed completely, rigorous curriculum design is a cohesive, interlocked alignment. Standards, evidence, and instruction are permanently connected. It forms a continuous improvement loop. Data from Stage 2 feeds directly back into Stage 1, forcing revisions for the next iteration. By engineering the authentic tasks first, we guarantee that students are equipped to apply their knowledge rather than merely consume it. Executing this architectural planning requires heavy lifting up front, but aligning your standards, assessments, and daily lessons is the only way to eliminate the activity trap. Whether utilizing a specific UBD template or an IB subject guide, the axiom holds true. To guarantee student understanding, you must build the curriculum backwards.